Right, folks, let's get going. So we were talking about constraints and triggers the last time around, and the fact that triggers allow you to express more action-driven bookkeeping operations to ensure that your database state stays in a consistent, in a desirable sort of scenario at all times. This was one sort of trigger that we looked at. This was trying to record and keep a track of which bars were sort of increasing the price at any given point by more than $1. So once again, this trigger is expressed as an event, condition, action, sort of sequence. Here you're doing the event is after an update of something on something, so it's sort of after the update. These two lines allow you to encode the variables that you want to keep track of. Here you want to keep track of the old row and the new row, and you want to compare the two. And then this for each row allows you to operate at the row level as opposed to the statement level. So as opposed to operating on a set of tuples, you operate on each tuple one by one. The condition here was checking if the new price is greater than old price by $1. If so, the action was to insert it into this new relation called ripoff bars. Okay, so this was sort of the template. This is an example that we covered in the previous class. Now, an extremely important use case for triggers is as means to deal with modifications on views. Okay, so let's say you have, firstly, it's tricky to modify a view because it doesn't exist. You don't have the data. It's a virtual table. But the instead of, as opposed to after or before, this is in the event clause. The instead of trigger allows you to intercept the modifications that are happening to the view and instead have it happen to the base tables. Okay, so you prevent the modification that's happening to the view, translate it into modifications that are happening on the base tables. Okay, clear so far? Okay, so let's say I have a view. This view was called Synergy. Synergy was is trying to record the drinker beer bar triples such that the bar serves the beer, the drinker frequents a bar, and the drinker likes the beer. Okay, so there are three relations here. Actually, I'll get to that in the next slide. Three relations: likes, sells, and frequents. So frequents was bar, comma, drinker. Sells was bar, beer, price, and likes was beer, drinker. Okay, so these are the attributes. Now, essentially what I'm doing in this part of the query is to do a natural join of these three relations, right? So I'm saying, let's do a natural join between likes, sells, and frequents. Frequents.drinker is, let's see, frequents.drinker is equal to likes.drinker, sorry, yes. Frequents.drinker is equal to likes.drinker, these two are related. Likes.beer is equal to sells.beer, these two are related. And sells.bar is equal to frequents.bar, so these two are related. So we're just ensuring that all of the attributes that are in common have the same values. Okay, so this is essentially a natural join of those three relations. Okay? Good so far? Okay. So the view then is basically selecting the drinker, bar, and beer. It's not selecting the price, but it's selecting the drinker, bar, and beer. Okay, so it's just selecting these three attributes. Again, this is just an example to illustrate what happens when view modifications take place and how do we intercept them and translate them into modifications on the underlying relation. Okay, so once again, this is just an example of a view. So like I said, this is a natural join of likes, sells, and frequents. And here I have picked, let me erase this, I have picked one copy of each attribute except for price. So now I want to allow modifications into synergy. Okay, synergy is a view. Synergy doesn't exist. It is a virtual table. So since I can't allow inserts, for example, into synergy, I want to use an instead of trigger to turn a drinker bar beer triple into 3 insertions, one for likes, one for cells, and one for frequents. Okay, I want to take this tuple that's being inserted into the synergy and then translate it into the three inserts that are going to happen on the 3 relations. Unfortunately, since I don't know the price, I'm going to set that as null. Everything else I know the value of because the synergy has values for drinker, bar, and beer. Right? So since it has all 3 attribute values as part of the view, everything apart from the price I can actually come up with values for. Okay? Yes? All right. So here's the trigger. So the trigger is named view trig, and once again I'm going to annotate this as C. I guess there's no C here, so it's just EC. C is empty A. Okay. So the trigger says instead of insert on synergy. So intercept and insert into synergy, and instead do something else. Okay, so this is the event. Then what I want to do is for every new row that is inserted into synergy, I want to insert it into the base tables, right? So this is a row level trigger rather than a statement level trigger, right? So I want to do some operation for every single row that is being inserted into this synergy relation, right? So think of this as a virtual relation synergy. I have some inserts happening into synergy, and I could have multiple inserts. And for each of these inserts, I want to instead translate this into an insert into the 3 relations, right? So I have, and then I want to do the same thing for the second insert, and the same thing for the third insert, and so on. Okay, so I want to do this for every new row or every new tuple. So I want, I'm referencing each new row as n. Okay, and then for every single new row, so once again these are both mechanisms that allow me to operate on one row at a time. For every new row, I'm going to do a certain action. Here there is no condition because I don't need a condition. I want to do this for every single tuple. Okay? I want to do this for every single tuple, therefore I don't need a condition. And the other thing that if you remember from the previous class, if I wanted to do more than one action, I use the begin end statements to ensure that I'm doing more than one action. And then I could have multiple actions within this begin end statement. So the 3 things that I need to do are to insert into cells, frequents, and likes, right? These are the 3 things that I need to insert. So I will insert into likes values n.drinker, n.beer. Insert into frequents values n.drinker, n.bar. Those are the 2 easy ones. And then insert into cells. Here I'm mentioning the bar and beer because I don't know the value for price. So I'm explicitly saying, you know what, I'm only providing the value for bar and beer. I'm not providing the value for price. Okay, so this is a little different from the other 2 inserts just because I'm not spelling out the value for price. And since I don't know the value for price, I'm just going to go ahead and list out the other attributes that I know the values for, and then list out their corresponding values. Yes?
What happens if the cells relation already contains that bar and beer?
What happens if the cells relation already contains that bar and beer? So it's just going to get inserted with a null value. So remember that at least in relational algebra, we had the issue of removing duplicates. In regular SQL, we are using a bag oriented notion. So you could have duplicates. These are not technically duplicates because they don't share the same price anyway, but you can easily go ahead and add multiple tuples like this. There's no problem. Even if you inserted the same tuple multiple times, it's just going to be there as multiple copies of the same tuple. Okay. Any other questions? Okay. So that's it with triggers and constraints. So I'm going to switch over and talk about a very different topic. Do you guys have any questions while I switch? Okay, so we are now switching over from a topic that largely is viewed as a database user's perspective of a database to something in between. So this is both important for a database user as well as a database developer. Okay, so indexing is a topic that is in some sense inside the database enough that you're going to understand how the database system thinks about, represents data, and accesses and retrieves data. So it's sort of somewhere on the boundary of user-facing and system-facing. Okay, so we are in some sense switching gears from just being able to sort of sit on top of the database and query it, which is what we've been doing so far, and peeking under the covers a little bit. So this is our first topic that is essentially trying to peek under the covers. Okay, so let's get into it. So the topics that we're going to cover within this indexing component is going to be what is an index, how do you build an index, and how do you maintain an index as more data is added. Okay, so that's the high level outline for each of the multiple types of indices that we are going to cover. So what is an index? An index is basically a way to look up data items, right? So you've seen indexes in textbooks. It's just a mechanism that allows you to look up where certain data items are located. In this case, an index in a textbook is basically telling you, hey, you go look at this page number, and this page number has the data item that you care about. Okay? So similarly, an index in your database allows you to look up where data items are located. It speeds up the identification of data items that match certain criteria. Okay? More specifically, an index is speeding up selections on the fields that you're searching on. So these are the search key fields. Okay, and so an index is built using a set of search keys, and these search keys can be any subset of the fields of a relation. Okay? For instance, let's say I have a student relation, and I may have a UIN, I may have an email address, I may have age, blah, blah, blah. Right? And I may choose to have an index based on, let's say, the UIN. Okay? If I'm choosing to have an index on the UIN, what that means is the UIN is the search key for the index, and then the UIN will be used to retrieve appropriate student records that match that UIN. Okay, so you can think of an index as being some structure that you say, hey, I want to find UIN XYZ, right? Find me the student with UIN XYZ. It's going to tell you, you know what, it's this tuple that corresponds to UIN XYZ. Maybe that tuple has XYZ as a UIN, email is xyz@illinois.edu, age is something, and so on. Okay, so that's a way to think about an index. You issue queries to that index using the search key field, and the index is going to look up stuff and give it to you. Okay, so a search key is any subset of the fields in a relation. It's not just one field, it can be multiple fields. So you could have an index on UIN comma email, right? You could have an index on both of those, in which case you have to provide the pair of UIN and email, and that becomes something that you are indexing on, right? So you provide that value, and once again, the way to think about that would be you have, let's say, this black box structure where you provide the UIN and email, and it will return you the tuple that matches it, that matches the UIN and email. Okay? If there are multiple tuples that match the UIN and email, it will return all of them. Okay? Clear so far? Just like in an index in a textbook, if there are multiple places where a certain concept is located, it might list multiple page numbers, right? Just like that, here if there are multiple tuples that match a certain search key condition, you will return multiple tuples. Okay? So the search key is not necessarily the same as a key. It could be a different set. Let's say I want to look up students by their major. Then I can certainly have an index based on the major, right? So, and if I probe my structure and say, give me students with major is equal to CS, it's going to give me all of the students who have major is equal to CS, one by one. Okay? So, it's just a means of identifying records that match certain search key values. Okay? Search key is once again a collection of fields, it's a collection of attributes, a collection of columns. Okay? So, entries in an index conceptually can be viewed to be the search key, it's a pair, the search key which is K, and R, which is either the record or the record ID or the record IDs or pointers. Okay? So, the second part of an index entry is fairly general. It could either mean the record, in some cases it could mean a single record ID, in some cases it could mean a collection of record IDs, or it could mean a pointer to where a record is located, or pointers to where records are located. Okay, so either way, the details are not important right now. What is more important is conceptually how do you develop these indices that help you retrieve records that match certain conditions in certain fields. Okay, so why is indexing important? Well, look at all of the SQL queries that you've developed so far, right? Most of the SQL queries that you've constructed so far have some where clause, right? They have some where clause. Therefore, they are selecting tuples based on some condition. If you are selecting tuples based on some condition, you need to have a way to in a fast manner retrieve those tuples. Indexes do just that. Okay? So indexes allow you to retrieve tuples in a fast manner from your database. Okay? So hopefully at least at a high level you understand what an index looks like. I'll get into the details and it'll become hopefully a little bit more clear as to what I'm talking about. But at a high level is this concept clear? Okay? Alright, so there are multiple sort of physical components to an index. From the index standpoint, there is an index file. This file contains the index, and this conceptually contains all of the information that is necessary to look up stuff in your data. Correspondingly, there's the data file which actually contains the data itself, right? So this data file has the data corresponding to a relation. In both of these cases, both the index file and the data file are organized in smaller units called blocks. Okay, so you can think of this data file as being one giant file, but this is organized into groups of in a granularity which is called blocks. This block could be of size 4 kilobytes or 8 kilobytes. Again, drawing an analogy to a textbook, you have your granularity could be a page, right? A page has a certain amount of information, right? And your index is also another set of pages. It's also organized as pages. So just like in this case where you have a file and blocks, in that case you have a collection of pages which correspond to the data part of it, which is the textbook part of it, and a bunch of pages corresponding to the index part of it. Okay? So in both cases, the index and the data file, you have blocks. These are the smaller granularity units that we operate on. So there are many different types of indices, and again, in this class, we are not going to be able to get into a lot of the implementation level details, but we will give you a sense for how these indices are built, how they are maintained, and so on. And again, we won't be able to cover all possible types of indices. We're going to cover a small subset of the most important ones. So there are two types of indices, or at least there are many different ways to organize types of indices. One of them is clustered versus unclustered. Clustered indices basically say that the records are sorted in the search key order. Unclustered indices are when the records are not sorted in the search key order. When would it make sense to sort the records in search key order? For instance, let's say my search key is a UIN, and I might want to store the list of students in sorted order based on UIN. If I have my data file, which is the list of student tuples, sorted in sorted order based on UIN, that means that the data is clustered on that search key. In this case, the search key is UIN. Okay? Clear so far? All right, so that's clustered versus unclustered. Another distinction is dense versus sparse. Dense basically says that every single record has an entry in the index. That's a dense type of index. Sparse is only some of the records in your data file have a corresponding entry in the index. Again, if these terms are not super clear to you yet, don't worry, we'll look at examples where it'll become a little bit more clear. The third distinction is between primary and secondary indices. Primary indexes are built on the primary key. Secondary indices are built on other attributes. Okay? Of course, there are some textbooks that actually interpret the notion of primary and secondary indices a little differently. But so just keep that in mind when you're looking at this distinction. This is not something we're going to be focusing on that much. We're going to be focusing more on these two. The last, which is also something we're going to be focusing on, is a type of index structure. There are many different types of index structures. There's a B+ tree, there's hash tables, there is R trees, there's a whole bunch of different index structures that people have developed over time. We're going to be covering at least these two, B+ trees and hash trees. Most of the other structures we won't have the time to cover. Okay? Okay. So let's talk about the first two notions here. There's a clustered and unclustered notion and dense versus sparse notion. I wanted to just introduce what those notions mean using a simple form of index. Okay? So let's say I have my data and index in this manner. This is my data file. This is my index file. Okay? And this is clustered. Therefore, the file is sorted on the index attribute. So as you can see, the data is in sorted order on the index attribute. And at the same time, it's dense because I have a pointer to every single record in my data file. Okay, I have a pointer to every single record in my data file, and therefore it is dense. Now, the next notion that we should be clear about that we introduced earlier is the notion of a block. Both the index file and the data file are organized in terms of blocks. Here, one block for the index would be this. This is another block. In terms of blocks for the data file, this is one block, this is another block, this is another block, and so on. So as you can see, you can have more information about more tuples within an index than within a data file. This is obvious because the index only needs to store the value for the search key field and a pointer. The data file may have hundreds of attributes. If it has hundreds of attributes, you're obviously not going to be able to store that many tuples within each block, right? So here you have information about 4 different tuples in a block. Here you only have information about 2 different tuples in a block. This is because the data is typically longer than the amount of space it takes to store one pointer, right? Here you're only storing one pointer. Here you may have many different fields. Okay? Yes?
So you're saying that a block is always the same amount of physical memory?
Typically, a block is always the same amount of physical memory. Yeah. So the reason why we think of things in terms of blocks is because this is the granularity at which you retrieve information from disk, and this is kept fixed. This is the and so you may be retrieving information from disk for your data, and you may be retrieving information from disk for your index as well. So it's always the same granularity. These it's all information, so it's treated alike. So the block granularity stays the same. Any other questions? Anything else? Okay. Right. So so this was a cluster dense index. Even though I did say that the blocks are the same size as the data blocks, there are much fewer numbers of index blocks as compared to data file blocks, right? So the number of this is weirdly worded. So the number of index blocks is much smaller than the number of data blocks, and therefore the entire index may end up fitting in main memory. Okay, so we'll work through a calculation that will hopefully illustrate that that is actually the case. Okay, so just like we saw here, we recorded information about 8 tuples in 2 blocks here, while we needed 4 blocks here, right? So just like that, you may be able to have it's typically true that the number of index blocks is a lot smaller than the number of data blocks, and because of that, the index blocks are often small enough that you may be able to fit it into main memory. Okay? Okay. So let's look at the other variants, the clustered sparse index. So the clustered sparse index would be, once again, it's clustered, so it's ordered by the search key attribute. So once again, it's ordered by this search key attribute, but it's a sparse index, so you are not storing a pointer for every single tuple or every single unique value. You are storing a pointer corresponding to the lowest search key in each block. Okay, you're storing a pointer corresponding to the lowest search key in each block. Here you're storing a pointer corresponding to 10, here you're storing a pointer corresponding to 30, here you're storing one corresponding to 50, and so on. So you're not storing a pointer for 20, you're not storing a pointer for 40 or 60. Okay? And the reason why this is okay is, let's say I wanted to look up the tuple corresponding to value 40. Okay? The way I would do this is to say, maybe I might go down this list. I might find that there is a pointer for 30 and there's a pointer for 50. Since I know that 40 lies between 30 and 50, I will need to start at the record corresponding to 30 and then work my way down up until the start point for 50, and at that point I can stop because I know that I'm not going to find any records with search key equals 40 after that. Yes? Make sense? Okay, so let me try to say that again. So if I wanted to find the record with search key 40, the way I would do that is to find a pair of search keys such that 40 lies between them, and then I would start at the lower search key and then work my way down the data blocks, right? So here I would find that 40 lies between 30 and 50. I would start at the record corresponding, or the block corresponding to 30, and then I would work my way down up until I hit the block corresponding to 50. Once I've hit the block corresponding to 50, then I know I'm done, because everything below this is going to be 50 or greater. Right? Everything below this is going to be 50 or greater. Yes?
But you can only use that strategy because we know it's clustered, right?
Yes, you can only use that strategy because you know that it's clustered. Absolutely. Yeah. Cool. Anything else? Okay. So, so far we've assumed that the keys are unique, but what if there are duplicate keys? So here's a clustered index, clustered dense index with a duplicate key. So unlike the case where we had, if you had unique keys, you would, in a clustered dense index, you need to ensure that every single tuple has a pointer associated with it. In this case, you don't need to ensure that. A clustered dense index only needs to ensure that you have a pointer for every single distinct key value. Okay, you have a pointer for every single distinct key value. So the distinct key values are 10, 20, 30, and 40. So your clustered dense index would have one pointer for 10, one pointer for 20, one for 30, one for 40, 50, 60, 70, 80. Okay, so you have one pointer for each distinct value, and it would store a pointer to the first record that has that key. Okay, so why is it okay to skip pointers for the other guys? Why is it not necessary to store the pointers for the other guys, like these ones or these ones? Why is it not necessary to do so? Yep.
Because we're clustered, so we're still in order, so you can just find the first one with that index?
Absolutely. So typically, when we are retrieving records with a certain key value, you want to retrieve all of the records with that key value. So you might as well start at the earliest possible record with that key value. You know you're clustered, so you can then scan down from that point, and you can retrieve all of the records corresponding to that key value, and you're done, right? So having those extra pointers is not going to help in any way. Okay, so typically when you're retrieving records corresponding to a key value, you are retrieving all of the records at once, right? Since you're retrieving all of the records at once, you might as well start at the earliest possible records that matches, and then go through the list and retrieve all of them that have the same key value, and then send it upstairs. Okay, so that's why it doesn't help to have additional pointers for every single tuple in this case when there are duplicate keys. Yes?
So there can never be like an instance where it's pointing to, like, it's pointing to the wrong index, like the middle one, say, instead of the first one.
So, okay, so the question is, do we have, what if this, instead of pointing to the first one, it ended up pointing to this one? So typically what we would try to ensure is that as data modifications happen, this constraint is met, which is that it points to the first record with that key. So we will try to ensure that that always holds, so you will never get into this sort of a pathological condition. If this sort of a pathological condition occurs, then you're in bad shape. You're out of luck, right? So if you're assuming that this is going to be the first record that has a key value, then you're not going to be looking up, you're going to be looking down. Right? So as long as at least in the algorithms that we are going to develop, we are going to try to ensure that these structures have some properties that hold, like this property. Any other questions? Okay. All right, so what if instead of a dense index you wanted a sparse index? Here one candidate would be to have a pointer to the lowest search key in each block. So does this work or not? So that's the question. Does this satisfy our needs, or are we going to run into some trouble? Yep.
Well, for the example with 10 here, aren't we storing too many pointers now? Or, I mean, it doesn't really matter.
So the point is, so what he raised was for the case with 10, aren't we storing too many pointers? That may be the case, but there's a more primitive issue that we'll get to that in a second. There's a more primitive issue here that if you stare at this for a few minutes, you'll figure out. Yep.
You're not pointing to the first 20 that exists.
Exactly, right? So you're not pointing to the first 20 that exist. So saying that, hey, I'm going to have a pointer to the lowest search key in each block is not going to be sufficient, because you are not pointing to the first instance of 20. So ideally you would like to point to the first instance of 20 so that you can start scanning from that point. That's not what is ensured by this. So how do we fix this? So one way to fix it is to have a pointer to the lowest new search key in each block. For this block, the lowest new search key would be 20, and therefore you can sort of have a pointer to this block that allows you to start your search for records with search key value 20 at this block. Now coming back to his point, wouldn't this still have the issue of too many duplicate keys? Yes, it might have an issue of duplicate keys. In the case when there are duplicate keys, you can get rid of the repeated entries, and it would still give you some benefits, because you can still start scanning at the first block that satisfies your search key condition, and then you go down the list. Okay, just like we did with the case where there are no duplicate keys, you can once again get benefits by listing the first record that satisfies your first block that satisfies your condition, and then scanning down. Okay, any questions? So one thing to notice here is that there are some, because this is a sparse index, there are some key values for which there are no pointers. For example, for 35, you don't have a pointer here because this is not the lowest new search key in that block. Okay, since this is not the lowest new search key in that block, it does not have a pointer to it, right? Which is totally fine, because we are in the sparse index regime. We are not in the dense index regime. If we were in the dense index regime, we needed to have a pointer to this. All right? Yes? What if there is another 20 in the third block? Okay, so let's say this was 20 instead of 30, and this was 30. Okay, so in that case, what I would be, at least this design would be storing a 20 here, because that's the lowest new search key in that block. But like I said earlier, an optimization is to get rid of this entirely and say, look, this is redundant because I'm already storing the information for the first block that contains 20. So I don't need to store this record, because I can, if I want to find all the records that match 20, I can start here and then go down. So I will anyway hit this block. Yeah? Okay. Now, for unclustered indices, we the first thing to remember is that unclustered indices are always dense, right? Why are unclustered indices always dense? Yep.
Because you couldn't
This is big, exactly. So so what he said was you can't use the scanning strategy of starting at a record and working your way down because there are no properties that hold between these records, right? You can't assume that they're monotonically increasing in search key field number, and because it's unclustered. Because it's unclustered, there are no relationships between the search key values of records within a block, so you can't use that sequential searching strategy. And because of that, you need to have a pointer for every single record. Okay, so because of that, you need to have a pointer for every single record, and because of that, unclustered indices always have to be dense. They can't not be dense. And unclustered indices are often used for indexing other attributes than primary key. Typically, what we end up doing is we cluster based on primary key, and we may have an unclustered index on a different attribute. For example, you may be clustering your relation based on, let's say, UIN, your student relation based on UIN, because that's a natural sort order for your student relation. But you may have an unclustered index on major, right? You have an unclustered index on major that will help you look up all of the students that satisfy a given major, but that is an unclustered index. Okay, that won't be a clustered index because a relation can't be sorted on two different criteria. It has to be sorted on one criteria. Okay? Any questions about this? All right, moving on. So one way to visualize or think about unclustered versus clustered indices is as you have a bunch of these data blocks. They are sorted in a fixed sequence, and therefore the pointers that you have is also in sequence in some sense, right? So if you think about the pointers that you have from the index to the data block, they're also in sequence. On the other hand, in the unclustered case, these data blocks are not in any particular sequence, so the pointers can be going in any and all directions, right? So you could have a record corresponding to one given value here, here, and here, while the next value could have a record here, and so on, right? So it could have, there's no given sort of ordering to the records in the unclustered case, so the pointers are in some sense flying in all directions. Now, let's focus more on the what the index structures end up looking like. So here, as you can see, I'm depicting the index structure as some form of a tree or a triangle, and we'll talk about why that makes sense in a little bit. But one last thing I want you to remember is whatever you're storing that corresponds to the index is all stored in one index file. Whatever you're storing corresponding to the data sits in one data file. Once again, that file is broken up into blocks. Okay, so let's dive into B plus trees. Okay, so B trees or B plus trees, the intuition behind B trees or B plus trees is that if you thought about the previous index structure that we had, you may still have, let's say you're talking about UINs, right? There could still be a very large number of UINs in your student database, right? There could be, let's say, tens of thousands or hundreds of thousands of UINs in your student database. So how do you retrieve a specific UIN? Going through the list of UINs is not going to be helpful because there could be a very large number of UINs. So what you might want is to have an index of an index, right? So you might want to have an index that tells you which index entry in the next level I need to look up in order to find a specific UIN. And then you might want an index of an index of an index, right? So you might want to keep layering on indexes of the previous layer. And that motivation, in some sense, is what leads us to a B plus tree. So this is a multi-level index. At the bottom, you have the data blocks. Next level, you have a bunch of index blocks. Next level, you have a smaller number of index blocks. Next level, you have a smaller number of index blocks, and so on. And so the way to think about this is an index. These are indices of indices. These are indices of indices of indices, and so on. Okay? So, so how do you go about creating this is going to be our focus. The textbook refers to B plus trees as B trees. Don't worry about this distinction. This is not going to be our focus. A second focus for at least our lecture today is going to be on the dense version. Then the dense version, of course, applies to both the clustered and the unclustered settings. The second constraint that we are going to be focusing on is the constraint when all of the values are unique, okay, not when the values are duplicated. Again, this is just to simplify the presentation, hopefully give you a broad idea of how these B plus trees look, not about very minute implementation details, which is not the goal. Okay, so any questions about that so far? I'm going to dive into B plus tree details. Okay, so B plus trees are trees, like the term indicates, with nodes that contain keys and pointers. Okay, so it contains both keys and pointers. These pointers can be to other records if the node, other nodes if the node is an internal node, or data records if the node is a leaf. So you can visualize this as a tree. You have, if your node is here, you have pointers to other nodes. If your node is here, you have pointers to data blocks or data records. So an internal node would look something like this. You have key values. In this case, there are 3 key values, and you have 4 pointers. So the pointers basically are interpreted in the following way. Everything up until the value 30, not including 30, can be found by looking at the leftmost pointer. Everything between 30 inclusive, but not including 120. So everything between 30 and less than 120 can be found by looking at this pointer. Everything between 120 and 240, so 120 can be found by looking at this pointer, and everything from 240 onwards can be found by looking at this pointer. So it will be x is greater than or equal to, okay. So this is how an internal node looks like. The leaf is a little different. So the leaf has keys as before, but has pointers to data records instead of ranges. In this case, these are ranges that allow you to fine tune your search. This is instead pointers to data records. So you have a pointer corresponding to 40, a pointer corresponding to 50, and a pointer corresponding to 60. Furthermore, you have a pointer corresponding to the next leaf in your bottommost layer. Okay, is this clear? Any questions about this? Yes.
So the degree of the B tree, is it just we just choose it?
Sorry, say that again.
The degree of the B tree.
The degree of the B tree. Okay, so that's something I'll get to in the next slide. So the degree of the B tree is going to be fixed through the B tree, and that's something I'll get to in the next slide. Any other questions about the basic structure? So the internal node basically subdivides a range into chunks. So in this case, you've subdivided into everything below 30, something between 30 to 120, something between 120 to 240, and then 240 onwards. The leaves basically have pointers for each key. So you have one pointer corresponding to 40, one corresponding to 50, one corresponding to 60. Okay? And then lastly, you have a pointer to the next leaf. The reason why we have this pointer to the next leaf is, let's say I want to find all of the records between, I don't know, of students between ages 18 to 22. Okay? So if I wanted to find the ages of all students between ages 18 to 22, and age is the search key, in that case, I may end up at the last pointer in my leaf. Instead of going back up the tree and coming back down to the next leaf, I can instead, having this pointer to the next leaf allows me to essentially sequentially scan through the leaves, right? It allows me to essentially sequentially scan through the leaves, getting to the next block or the next record in sorted order. Does that make sense? So I have 40, 50, 60 right now. If I wanted to get the next record in sorted order, I can just follow the pointer to the next leaf and do that, instead of going back all the way up to the tree and going back all the way down. That's another strategy, but instead this would be faster, right? Because it's just one pointer jump. Okay, so let's get into the issue of degrees. Okay, so you have this parameter called d, which is the degree. D is the minimum amount that any node needs to be filled throughout your B tree. Okay, it needs to be D or above at all times. M is the maximum number of keys that can fit in to your internal nodes or to your leaves. When M is even, this is going to be our focus. When M is even, then each node has between D to 2D keys, and M is equal to 2D. Okay, so M is equal to 2D. Each node has between D to 2D leaves, D to 2D keys. All nodes except for the root. Okay, all nodes except for the root are going to be at least half full. Okay, and we are focusing on the case where the maximum number of keys in a node is even, so M is equal to 2D. But even if it is not even, you're still going to maintain the condition that it's at least half full at all times. That is a condition that the B tree is ensuring. Our focus in this lecture to simplify presentation is going to be the case where M, the maximum number of keys that you have, is even, not odd, because it will help us work through what happens in a much more easier fashion. So again, this is just to illustrate the concept, not to illustrate the nitty-gritty details. In the textbook, you will find the use of ceiling symbols, floor symbols to deal with the odd and even issues differently. We don't want to worry about that. Instead, we are going to focus on the case where M, the maximum number of keys, is even. This is twice the degree D. D is the minimum amount that each node needs to be filled in at all times. Okay, so irrespective, you want your node to be at least half full at all times. D is the minimum amount it needs to be full, and we are going to be focusing on the case where the maximum number of keys is 2D. So at all times you have between D and 2D keys in each node, okay, be it internal or leaves. Okay, D is called as your degree of your B tree. The textbook, like I said, uses n+1 to denote 2D. This makes the math a little bit more hairy, so that's why I'm using a simpler way to reason about things. But beware that it uses a different notation, but it's essentially the same idea. Okay? Okay. So let me keep going. So I have D is equal to 2. I need to ensure that there are at least 2 keys. So one thing that I failed to mention was that this does not hold for the root. This need not hold for the root. Root does not have this condition. Root can have 1 key, and that's totally fine. It does not need to have at least D keys at all times. That's not necessary for the root. Okay, so here's an example of a B plus tree. The root can have 1 or more filled in keys. The rest of the nodes have at least D keys that are filled in, and the maximum number of keys are 2D. Here in this case, D is equal to 2. The maximum number of keys is 4, because there are 4 slots here, as you can see, right? So the root in this case has only 1 key that's filled in, and that's totally fine because the root is special. For the other ones, as you can see, this has 2 filled in, this has 3, 3, 4, 2, 3. All of them have at least 2, so we are in good shape. So this is a valid B plus tree. Okay? All right, so as you can also see here, you have, these are the internal nodes. So this is an internal node, this is an internal node, this is an internal node. And these are the leaf nodes, right? So 1, 2, 3, 4, these are the leaf nodes. And as you can see, for the internal nodes, if I were to follow this pointer here, this would be between whatever and 80. This would get me to everything 80 onwards. Okay? So everything up until but not including 80 you would get from going down this path. Everything 80 or above you would get from going down that path. Okay? And then similarly for the 20-60 case, everything up until 20 you would get from going down that path. Everything between 20 to 60 you would get from going down this path, and everything 60 above you would get from going down this path. Okay? All right. Finally, for the leaves, as I mentioned earlier, you have one key and one pointer to one record for each of those keys. So you have one key for 10, 15, 18, and you have one record for each of those values. And again, remember that there's a pointer to the next leaf, because that will allow us to essentially sequentially look up all of the records that satisfy a certain range of values for your search key without having to go back up the tree and then back down. Okay, you don't need to do that. The next pointer allows us to scan the records roughly in sequential order. Okay. So, hang on, just give me a second. Okay. All right. So the any question about this overall architecture of a B tree so far? Okay. So let's talk about how large does the B tree, how large can D be in order to be able to respect the constraint of your block size. Your key is typically 4 bytes, your pointers are typically 8 bytes, and your block size is typically 4 kilobytes, so 4096 bytes. And so you have 2D up to 2D keys and up to 2D plus 1 pointers, right? So 2D times 4 plus 2D plus 1 times 8 is less than or equal to 4096, and therefore the maximum number of keys that you can have are 340, and you have up to 340 records in the leaf blocks. Okay, so remember that the leaf blocks have 2D pointers to records and 1 pointer to the next leaf, while the internal nodes have 2D plus 1 pointers to other internal nodes. Okay? So let's talk about searching a B tree. So if you wanted to look up a B tree for an exact key value, you would simply start at the root and then proceed down to the leaf. So in the case where you have a where clause like select name from people where age is equal to 25, and you have an index on the age is your search key, you go down this B plus tree with values equal to 25 up until you find the record that satisfies your condition. If you have a range query, you would similarly, so something like this, so select name from people where age is between 20 to 30, you would do the same like you did here. You would start with 20 and then you go all the way down to the bottom. Once you've gotten all the way down, you do sequential traversal at the leaves, right? So this is where the next leaf pointer is useful. Once you've gone beyond the other extreme, which is 30, you don't need to look at records any further, because you know that you're not going to find any other records that satisfy the condition. Any questions? All good? Okay. Okay. So one last thing that I wanted to mention before I get into the details of how to insert and search through a B tree is to talk about how large B plus trees need to be in practice in order to store information about records. So your typical D value, like we saw, can be as high as order of 100. Okay, so it's order of 100, let's say. Your typical fill factor is, let's say, 2/3. Okay, so it's around 66.6 or 66.5, in which case your average fan out is 133. Again, this is a very rough calculation to show you an indication as to how many levels of a B plus tree is needed to store information about a large number of records. Now, with a height of 4, you can store information for up to 312 million records. Okay, so just a B plus tree of size 4 can help you store information about such a large number of records. So that's impressive. And with one with level 3, you can store up to 3 million records, information of up to 3 million records with a B plus tree of size of height 3. Moreover, it's not just true that you can store a large amount of information with a small number of a small height of your B plus tree. You can often also store a large number of levels within your main memory, right? So for your first 3 levels, you can store all 3 of them. Again, I'll let you do the math, assuming the fill factor is 2/3, such that all of them can be stored within roughly 140 megabytes in your main memory. Often these days you have main memory sizes of several gigabytes, right? So I've heard of, at least in your laptops, you would have 8 or 16 gigabytes, and so you have a large amount of main memory that will easily allow you to store up to 3 levels of your B plus tree easily within main memory. And that will contain information about 2.4 million records. So that's impressive, right? So just with 133 megabytes, you can store information about 2.4 million records. Okay, so this is just an indication of how powerful B plus trees are, and in a small amount of information, they can store a large amount of, or small amount of storage, they can store information about a large number of records. Okay, so we've talked about searching. Searching was straightforward. You just follow pointers based on which direction, where your value lies in terms of the constraints. We saw these constraints, right? So you had, for instance, this was between 20 to 60. So if your search value lies between 20 to 60, you'll follow this path. Otherwise, you would follow this path. If it was less than 20 and if it was greater than or equal to 60, you'd follow that path, right? And this way, you would go all the way down up until you found records that matched your condition. Let's talk about inserts. In the process, we'll also talk about searching as well. Okay, so so the way to insert, let's say I have a new key K that I want to insert with a pointer P to the record that satisfies that key. I first find the leaf where K belongs, and then I'll try to insert that that record into that key and that pointer into that leaf. If I end up having an overflow, if I don't end up having an overflow, so it's still 2D keys or less, then I'm in good shape, I can stop. If there is an overflow, so it's 2D plus 1 keys, then I need to split the node and then insert an appropriate value in the parent. Okay, so let's say my 2D was 4, like in the previous case, I've gone and inserted something into a leaf. Now I have 5 keys and therefore 6 pointers Okay. Of course, one of these pointers could be a pointer to the next leaf. No, actually, this is an internal node split, so I'm wrong. So this is an internal node split. So so typically I would have 4 keys and 5 pointers, and by inserting one more node, I would have 5 keys and 6 pointers, right? In that case, what I would end up doing is to split it up into two internal nodes, such that 2 of the keys are in the first node and 2 of the keys are in the second node, with K3, which is the last key, moving up to the parent. Okay? And then half of these pointers, P0 to P2, end up staying in this node, and P3 to P5 end up staying in this node. Again, don't worry if this isn't clear right now. Just try to get a high-level idea of what's going on. We'll walk through an example and become clear. So, for internal node split, when the root splits, the new tree has one root only, right? So let's say this was the root and it was filled up, and you added yet another key to it. It's going to expand, split into 2. One key will become the new root, and therefore the new root has only one key, right? So the root is special for this degree satisfaction condition. All other nodes are have to satisfy this condition that they have at least D. The leaf node split, again, just bear with me through this and then we'll look at an example. For a leaf node, let's say you have, in this case you have 2D pointers to records, and so 2D in this case is 4, right? Sorry. 2D in this case is 4, and you have one extra pointer, and you have 2D keys, and you have one extra key. You would split this up into 2 leaf nodes, one containing the first 2 keys and the first 2 pointers, the second containing the next 3 keys and the next 3 pointers. So it's a little different from the internal node split, but it'll become clear why this is needed in when we look at an example. Okay, so an example in the next 5 minutes and then I'll stop. So let's say once again that D is equal to 2 and I want to insert K is equal to 19. Okay, so if I want to insert K is equal to 19, so I have a record with search key value 19. I'm going to follow down this path, right, because it's less than 80, follow down this path because it's less than 20, and then now I'm finally at this leaf. This leaf has space, so I'm actually in good shape. I just need to insert 19 here, have a pointer to my new record 19, and I'm done. Okay, so this is the easy case, right? This is the easy case. What happens when this becomes full? That's the interesting one. So let's say I want to insert 25. Go down this path because it's less than 80. 25 is between 20 and 60, so I would go down this path. Now I want to insert 25 into this. So I would, when I try to insert this, I have now more keys than I need, right? So I already have 4 slots, but I now have 5 keys. So what happens then, right? So I need to split this. Okay, so I need to split this. Since this is a leaf, the way I would split this is to split this up into 2 components, 20 and 25 in one, 30, 40, 50 in the other. So 20 and 25 becomes one leaf, 30, 40, 50 becomes another. Now when I split at this point, since I have 2 leaves, I need to make sure that this has pointers to both of those leaves, not just one of those leaves, right? Right now it only has pointers to the 20, 25 one. So I will go ahead and add an extra value 30 to the parent, which is the smallest value which I will find in the second leaf that was split. Okay, so remember earlier you had 20 and 60, so go back, 20 and 60 were the two values. You've gone ahead and inserted 30 because 30 is the smallest value in the new leaf that you formed. Okay? Yes?
Can you explain why we don't split with 40 instead?
Why you don't split with 40 instead? What do you mean by that?
So you know how you have 30 here with the split, before, so you split with 30, in a sense where 30 is the next, head, in a sense like the first two. So why don't you split with 40 instead?
So you're saying instead of splitting it with 20, 25, 30, why don't I do between 30 and 40? Yeah. I think that would work. This is just it's. It has to be somewhere in the middle. It can't be at between 40 to 50, right? Because that'll basically have one leaf with too few nodes. So it can't be between 40 to 50, but if you're splitting between 25 to 30 or 30 to 40, this is just convention that you split such that the left one has fewer nodes than the right one, but that's not a big deal. I mean, it's equally valid if you split it in the other way. But you need to still ensure that each one has D at the end of it. Okay? Okay, so, right. Okay, so then let's see what happens when you delete. Okay, so let's say I wanted to go ahead and delete. I decided to delete the value 30. How do I delete? Well, I go down once again this way, and this is the smallest one, this is where I would find values between 30 to 60, and then I want to delete this record. So I go ahead and delete this. I'm okay because this still contains two keys and two pointers, and therefore I'm okay. I'm still maintaining the condition that D is the minimum number of nodes or minimum number of keys is still 2. So I'm okay so far. So I can go ahead and delete. One thing that I can do if I choose to is to update this to 40, because 40 is now the smallest value that you will find in this internal node. But I can choose not to as well. If I don't want to do that extra work, I can leave it as is. It's not going to be wrong. But if I want to make search more efficient in the future, I might want to change that to 40. Okay? Okay, now let's see what happens when I try to delete 25. Okay, so I'm trying to delete this 25 value. What that ends up doing is it ends up, once again, reaching 25 is not hard. I would follow this pointer, and then I get to this leaf. Let's say I've gone and deleted the key and the pointer. Now this is imbalanced, right? So this is less than D. It doesn't have two keys. Now I need to do something. One thing that I can do is to simply grab some stuff from the left-hand side, because the left-hand side has more than enough stuff, such that this leaf once again has D keys. I could technically also grab from the right-hand side, but this right-hand side has far too few, right? It has just exactly D. So I can't grab stuff from the right-hand side because the right-hand side would end up violating the constraint. So in this case, I grab stuff from the left-hand side. So this is a rotation operation, and once I rotate, like I said, rotation can involve either sibling. Here only the left sibling can help. The right sibling has just D, doesn't have greater than D. So I rotate from the left sibling. I grabbed the key value 19, so that this leaf now has exactly D. I now have to now notice that this key is stale. It's not correct anymore because 19 is the smallest value in this leaf. So I have to go ahead and update this to 19. Okay? All right. So I think I should stop now. I'll talk about the last case for deletion, which shouldn't take very long. But hopefully, at least, even though the conditions that we talked about were a little complicated, the example made it a little easier to understand.